on in. Let's make a start. Okay, I'd like to thank very much our next speaker, Sharad from University of California, Irvine, who's going to talk about challenges in scaling privacy-enhancing technologies to campus-level IoT, Internet of Things, Testbed.
Thank you. Thank you. Again, it's a great pleasure to be here. So I will talk about scaling privacy technologies to a campus-level testbed. And let me go ahead and say this. So at some level, integration, there's the aspect of understanding if privacy technologies work or they don't work in different settings. I think the message here is going to be mixed. Yes, they apply in a variety of different settings that I'll talk about. But can they be improved? The answer is absolutely yes. I think the more interesting part of the talk from my perspective is that if we start, so this is a system level talk about integrating technologies into a system. And the key aspect which I want to sort of drive out and tease out a little bit more is that if we integrate these technologies into the systems, some new challenges and new approaches come around. So there are some interesting challenges which probably one may not have experienced or seen before, which sort of pop out when you sort of try this integration. So that's what I'm hoping to achieve. Let's see how that goes. So let me first give you a bit of an introduction on IoT. IoT is ubiquitous. It's almost in every domain. As when devices and everything that you carry, your mobile phones are connected to the internet or a network, you have an opportunity of sort of creating systems which are smart, intelligent, adaptive, which can observe the phenomena of what's going on in the real world, and obviously use that to improve basically processes that go on, as well as to bring new functionalities. This is the next dominant wave, probably, which will maybe even dwarf the internet revolution that happened. The expectation is that very large, so there are already over 25 billion devices which are connected today, and this connection will continue on and on. The expectation is that very, very large amounts of data will be sort of generated from these different domains. These IoT domains are based around sensors. So sensors capture data about the environment, which obviously if there are humans in the environment, then you're going to have privacy issues that come in as well. The particular IoT setting, which I'll be sort of migrating towards, sort of talking mostly about, is more towards building management or smart spaces, such as this room itself. There is video cameras all around, so in some sense you're observing or you're also already sensing what's going on in this environment. So that'll be the focus that we'll sort of use in the stuff. So this is the concept of the testbed that we started off with the help of DARPA. And the idea was to take physical spaces, instrument sensors in it, and build a system so when data gets generated from these different sensors, it passes through a system. We do data management of the sensor data. Then we build applications and services on top of this particular system that we have. And we actually have real users use these services in real time in whatever, in their daily activity. And the goal was, in this setting was, the system that we build will infuse in it diverse privacy-enhancing technologies, and we'll talk about specifically what we have done in a couple of minutes. And the thought then was that if I take these different privacy-enhancing technologies, I can evaluate whether it's good or not good or how effective it is. So there's a technology evaluation aspect to it. One can even sort of understand user studies and say, OK, what do people perceive about, because they're using these applications in the context of, let's say, a system of this kind or testbed of this kind. So you can even do user studies to see what people's perception about privacy might be. And as I already mentioned, the interesting part from my perspective and from our perspective was research gaps. So there is one thing which is there's a lot of work which we've sort of, in the morning we've been seeing it, and I guess last 2 days has been seeing. There's a lot of interesting sort of work that's happening in the privacy domain. The question is, if I integrate this into a system, what actually happens, and are there other issues that come around? So that's sort of what we were after. So here's the outline of the talk. What I'll do is, it'll be sort of a bird's eye view of our talk. I'll talk a little bit about Tipper system to give you the context of what we are doing in the context of, and also a little bit of the testbed that we have at UCI. We look into privacy leakage from sensors. It should be relatively straightforward to sort of see that sensors which observe people at very fine grain have a significant amount of information captured about humans that leads to privacy inferences that can be made. So we'll have done a preliminary study of what the leakage is, And it actually relates back to some degree to Lee's talk as well, because she talked about trajectories and she talked about basically mobility patterns of people. So there's some relationship in that sense to this particular thing as well. Then we look into the challenges in deploying the privacy technologies at the campus scale. Specifically, we look into scalability as a challenge. So let me first start with telling you a little bit about Tippers. So Tippers is sort of the heart, the system is the heart of the testbed itself. It's the thing that does your data management. It gets information from diverse sensors, which flows in, and we do representation of this data. Now, the way we have designed this system from a system perspective is it's a middleware approach. So we get the data, we process it, we model it, we represent it, but when we want to store it, we send it off to a storage manager, which is typically either Oracle or MySQL or other systems that we will see, which are maybe secure computation systems as well. So we do that. The architecture of the system is plug and play. So the whole idea behind this was that we'll develop a plug and play technology where you can bring in different diverse privacy technologies and integrate them inside. We don't necessarily develop all these things ourselves, but we sort of borrow from a lot of people, actually a lot of people in this room itself as well. And specifically, all right, so before we go into the privacy technologies, so the Tipper system has been built and it has been deployed in different places. It started off with being deployed in the building, the computer science building at UCI, which is the Bren Hall. And slowly it has sort of migrated towards or increased to about 35 buildings now. We get data from 35 different buildings, and sort of we have building services on top of the 35 different things, the buildings. And there are a variety of different services, and I'll show you a couple of more examples of that. These services range from real-time services, location-based services, to analysis, so building analysis kind of services as well. So a lot of these different kinds of services are built on top of essentially the campus testbed. The Tipper system also was ported and installed at Honeywell Golden Valley Lab, and what they did was they were trying to understand individual behavior from shared sensor data, and specifically they connected Tippers to about 2,000 motion sensors which are in their building, and the data flowed from that to Tippers, and they were, let's say, services on top of that they were built. It's also more recently gone to Spavor in the installation at Spavor in San Diego, where they have connected a variety of different other sensors like active badges, Bluetooth combined with, and they've taken this data that they sort of generate along with simulated data as well, which we generate for them for their particular, let's say, installation. And the goal there is to explore a slightly different twist, which actually I will not talk about today too much because there's ongoing work at this stage, which is on building monitoring services based on privacy. So this is the Spavor mobile land sort of installation is headed towards not about, let's say, data release or sharing of data to others, but really building monitoring services, real-time monitoring services using privacy technologies. So let me talk a little bit more about, because the context of this talk is going to be UCI testbed, so let me talk a little bit more about the installation we have there. So at UCI, we have a variety of different sensors, ranging from Bluetooth beacons, video cameras, power monitoring systems, and most importantly, the Wi-Fi access point data sets. So one of the advantages of the Wi-Fi access point data set is that if I sort of look at your connectivity data from the Wi-Fi access point, I do not need to install any software on your machine. So it's a passive sort of a monitoring device where I can sort of get a relatively inaccurate, but at some level, still localization information coming from the access point, which can locate you within a particular region where the access point is sort of there. Now, this information coupled with other information can actually provide, we've seen, and we've sort of looked at that, significantly more accurate, let's say, localization within buildings itself. The advantage being that I don't have to install anything at all to sort of monitor people in this case. So in other words, we can monitor thousands of people, as we'll see, basically without any installation of technology on their phones or asking them to do anything different at all. So we get this data, and this data is pretty sensitive, so naturally it is encrypted before it's given to us. There is a mechanism which sort of enables Tippers to go back to, if, for example, you want to use not general services, but let's say you want to use location-based services for your own, then you have to give us explicit consent, and then we'll go back to essentially the UCI level, let's say, where the data is collected, and show credentials to get actually data about you. So we can open the data that sort of relates to you. So we can offer you more higher level services. So when data flows in from different sensors, one of the main things we do is we create a dynamic map of where people are as a function of time. And based on your location, the data or the presence, we sort of convert that into occupancy, which is then at the spatial level. So in this room, there are 100 people. In that room, there are 50 people. Or in your office, whether you're there or not, for instance. So then that becomes occupancy. So as I said, we started with something which is in a single building. Now it's expanded. And the interesting part from here, which will be important later in the talk, is if you sort of look at the data sets, we are talking of roughly around 1 million events a day, location events a day. So we want to be able to scale pricey technologies when we sort of implement them in the context of something like this to adhere to or to be able to sort of tolerate that levels of workload. And then there are applications built on top. So an example of application is a concierge application where you come into the building, you want to find me, you can sort of, if I've given you permission, then you can track me in real time. You can also track which rooms are empty, where you want to sort of, you can do building analytics, all the other different, as you normally imagine, variety of different services. And one thing I should add is that once we build the system, we open the interface, give it to students to go crazy on it, and they build lots and lots of different applications, which is sort of on top of this data. Okay, so from a privacy technology perspective, Tippers has a variety of things integrated inside it. It has fine-grained policy, basically, which controls who has access to what data. I'll talk a little bit more about that. There is secure data management, which is when data comes into Tippers, it's encrypted, at least the Wi-Fi access point data, so then there's secure data management. Data from Tippers can go into the cloud. Again, we use secure data management for that purpose. There's differential privacy. We'll talk about that in a second. Actually, the people who did that work is also here. Jerome, Marshfin, and Michael, they're the guys who sort of implemented differential privacy. We took their work and sort of incorporated into our system. And then there's also resource discovery. So policies are integral to Tippers. It's all the way from every processing of data is based on policies. So what data gets collected, let me see if this works. What data gets collected, what data gets stored, how long is it stored for, what processing is allowed on it, or who can share what data with whom. Everything, let's say, data cycle in Tippers is controlled through essentially policies. For differential privacy, the place it's integrated is in the occupancy. So we have the pure occupancy that we have calculated from the, let's say, the presence data. Once we have our sensor data, once we have that, if we want to expose this privacy to others, or this occupancy to others, we sort of run it through a differential privacy algorithm. The specific algorithm we sort of integrated is a system called Pegasus, which was built by the guys I mentioned to you earlier. So we sort of integrate that as well. Again, Tippers has, when data comes into the system, it can be outsourced. The outsourced data can be in an encrypted form. So there are multiple different database systems which have been secure database systems that have been integrated. One of them is Pulsar. And the other one is Jaina by Galwa. All these systems support a variety of different cryptographic mechanisms. So for example, Pulsar has function secret sharing. It also has searchable encryption built in, and so on. Jaina is sort of interesting in the sense that it supports full-blown SQL queries on encrypted domain. It offers a variety of different sliding scale security. So you can store data in a pure in a plain text form. You can also use MPC engine, which is built on top of the Speeds engine as well. So you can do MPC computation as well. So you sort of get a variety of different, let's say, technologies with these things. Okay, so that's sort of enough as a background for what Tippers is. Let me go into a little bit more into inferences from sensor data. So when we started the project, the very first thing we sort of did was we went to UCI and got them to give us Wi-Fi access point data sets. And the question then that came up was that the university would not give you the Wi-Fi access point data set unless it is anonymized. So it is anonymized data. Now for this crowd, this will make absolutely no issue at all. Anonymization doesn't basically work. And one of the obvious things is that you can reconstruct from it basically when the people start arriving, when they don't arrive, when the day ends, and all that stuff. More interesting thing is even very simple classification techniques based on your patterns of, let's say, use or what you do in the building sort of can completely identify if you're a visitor. For example, if you're a visitor, then you connect with one access point, then you go away. If you're a resident, you probably are there for a longer time. So all these things sort of can be done. So classification of people into grad students, faculty, staff, all that stuff is relatively simple. Even straightforward SQL queries, which is what we ended up writing could classify them and get an accuracy level around 98% or so. So we didn't even have to train very complex models at all for this purpose. And once you have classification, you can do social media analysis, like social group analysis, who meets who, that kind of stuff. The question which came up at that time was, why is this interesting? Why is this important? And here are a couple of examples of why it's important. For instance, once I can track staff, I can figure out who spends how much time inside there. So the top graph is sort of showing a histogram of how many hours people spend and how many of them are sort of how many faculty spend, how many staff spend how much time. This can get sensitive. Here's the one which I sort of particularly, because one of them is me. So we also did another thing just to drive home the point to the people. So we sort of took once I've triangulated and figured out that this person is a faculty, and if I know the class schedule, then I sort of know when the faculty shows up in this particular, person shows up in that room, that's that faculty member. Once I have that information, I can start plotting things like, hey, how often are you late to your class? And that's what the graph is showing. The red means tardiness, and green is showing good, it's okay. So you can see that there's this guy in the middle who sort of is very often tardy, for example. So you can do all the interesting stuff. It's sort of driving home the point that there is interesting privacy questions, which you may, even in innocuous data such as, hey, location inside building, in a campus perspective, is actually a huge amount of privacy questions which come up. This is the study that was done by Honeywell to drive essentially similar points. I'm not going to belabor too much. Basically, they had the reason why there are differences is that in our case, Wi-Fi access point data sets are very personal. It's like one person. Like it's my data, my connectivity information, even though it's anonymized, it's about me. Here, it's about motion sensors, which are sort of installed all over the building. And the thing that shows was that if you take some information about basically people and their practices, using motion sensor data, you can actually pretty much figure out who's not coming a particular day, who's coming a particular day. That's the thing shown in the top figure. The part which is sort of interesting is the lower one. This is one specific motion sensor data. And there's a particular pattern to it if you notice. There is a time period which somebody is there, the motion sensor is on, and then it's off, then on, then off, and there's a repeated pattern. So I don't know if anybody can guess what that could imply.
Smoking.
There you go. It's exactly smoking. It's exact smoking pattern. So you pretty much know how much does the guy smoke. It's a real data. The guy had agreed to sort of share his data with us. It can be determined. So that was a study on motion sensor. The third study, which is the UCI part of the study, is more towards differential privacy. So what we did was we had occupancy data, and as I said earlier, we took Pegasus sort of Pegasus system, and we generated differential private occupancy data on top of it. And the question we were going to ask was, given that I have access to a occupancy data, how accurately can I now localize people or individuals based on this occupancy data? So the first question was, before we even study something like this, we have to have a notion of utility, because obviously I can just throw random noise and then everything will be totally private, right? So that is not the right thing. So we chose a particular application, which is the heat map of occupancy. And what we did was we sort of said, okay, there are going to be 5 colors in this heat map, so green all the way to red, showing the amount of people in the particular, let's say, location, okay? And if I sort of look at their 5 colors, if I were to randomly guess, it'll be 20% chance I'm going to get it correct. So the expectation is that without any data whatsoever, without any priors, without any knowledge at all, I sort of get 20% correctness anyway. The question was, let's set a bar for differential privacy to be a little bit, when I'm releasing data, to be a little bit higher from an application utility perspective. So we experimented with a few things. I don't know if I have the next graph to show that or not, but we decided to be not particularly aggressive about this matter. So we just said, okay, let's make sure that we get the utility of around 40%. So I want to set a threshold of epsilon to a differential privacy such that the utility at every instance of time remains around 40% or so. And this turned out from, I don't know if I have the graph right here. So it turns out that if you want that, the epsilon that I required in this case was at least 1. Now, that being said, it's possible that I could have taken a system such as Pegasus and could have trained it much better or whatever, done a little bit more post-analysis than we did to get higher utility. That's a possibility. But we didn't try that hard. We did try a little bit, but not that hard. So he said epsilon equals 1. So the question that came up was, all right, how much is now the privacy loss? How much can, if I output the location data at epsilon equals 1, what will be the location basically to what level can I guess person's location. So for this particular experiment, what we did was we took about 1 month of differentially private occupancy data from UCI, from Arbran Hall, and there are that many regions. So another question which came earlier in Lee's talk as well was the granularity aspect. So the question is localization of people to what level? At the level of the building, at the level of a floor, region, or maybe room. And so that's why it's important. There are 6 floors in that building, there are 23 regions and 334 rooms. So those are the number of events that happen. The methodology we used was the following. We sort of took the top 50 people who come to the building, and we sort of looked into the privacy or basic ability for us to guess the location of these top 50 people out of 21,000 people. Now, the reason we sort of did this was because the models that we are running behind the scene are very complex and sort of computationally extensive. So we had to choose something which chose the top 50. Yes.
Sorry.
Salil.
The epsilon that you're writing there, is that for the epsilon you're using for a single occupancy count, or is that a person level epsilon?
No, in this case, it's for the single occupancy. Like it's actually the system is generated using Pegasus. So Pegasus is a sliding window kind of a thing. So it takes a window and it publishes it for a particular window. And we vary the epsilon to a variety of different levels. You had a question? Yes.
So, how did you know who were the top 50 people with the highest presence in the building?
Oh, we have the data set, right? So we have the data set for, oops, sorry, where did it go? Yeah, 1 month differential private data, right? So before we have we also have the actual data as well. So we could figure out who are the top 50 guys who are sort of in the building.
Okay, but and by looking at their offices or something like that?
No, by looking at the real data. So I know that there's a guy who's, I'm looking at your connectivity information, so I know that you are occupying the most amount of time in that 1 month. So I have actual data as well, right? For the analysis, we sort of use both, the actual as well as the differential private one. Is it okay? Okay. All right, results, I guess. Okay, before you do that. So the main question, obviously, in any model of this kind is what's the prior? So we did not use a particularly strong prior. In this particular case, the prior is based on transition probabilities, which is, again, learned basically on the data itself. We did not customize the way Lee was trying to do for individuals. The prior is sort of a global model, basically, for everybody. So it's time invariant and individual invariant. And priors can be improved. There is a lot of work going on sort of trying to improve the priors itself. And for the posterior probability, there are multiple different techniques people used, but the one sort of which I'm reporting here is using particle filtering. So we sort of pushed this into the particle filtering sort of a system, and out came the output the probability of a person's location. Now, there are multiple different studies we did, but the one I'm sort of going to show a result on is an aggregated privacy metric. And the way we did this was the following thing. Given a granularity, let's say it's floor, whatever it is, at this granularity, if I look at the probability P based on the occupancy statistics, which is at a given probability level, and the probability level is divided into low, medium, and high. So how many extra people do I get to know them at a given level, which I could not based on priors? So if a prior already gave me information about you, so for example, if you're a printer and not a human being, so you're always in the building, the prior tells it to me already, right? You're not moving, hopefully, right? So then I already know that, so that's not counted, right? So I'm looking for how many extra things do I get to learn based on the differential prior data, which the prior would not actually offer to me. And the results were sort of here. So out of the 50 people, if you remember, the green is showing that of those 50 people during the time period, how many were there in the real building. The red is showing what are the extra people we could get to know at medium probability, and the purple is showing at the high probability. And what you get to see, though the numbers don't show up that clearly in the figure, is out of the 50, about 4 or 5 people's private location was sort of known to us based on the model we had, based on epsilon equals 1 in this case. So I think the main point of this study was that, yes, privacy is a challenge, and there is a room for sort of improving things. Okay, so I'm going to push to the third part of my talk, which is on challenges in deploying privacy technologies at campus scale. So if I look at deployment of privacy technologies, and for us, the privacy technologies are not just differential privacy. In fact, today I'm not going to talk much about differential privacy. It's also secure computation. It's also policy management. And the question is, what are the challenges that come when you try to do any of these things? First question that shows up is the scalability challenge. And the question is, given the scale of data and queries, can you actually scale the secure computing technology to that level? And we'll see a little bit of work on that direction. Similarly, for policies, policy in the IoT spaces are going to be very fine-grained. And if you have fine-grained policies, can today's database systems, which do support policy management or policy engines, can they actually do real-time enforcement? And likewise, from the differential privacy perspective, given the applications that are asking complex queries, can you do this in a meaningful way while still ensuring some level of privacy of people? So we sort of made a little bit of progress in each of these different things. The last one is sort of collaboration with Ashwin's group, which is on one side differential privacy. And I'll maybe refer to it in a minute, and maybe if not, we'll see. All right. The second challenge, which is also equally important, is that of interoperability. It's not about scalability, but interoperability. So specifically, if you take differential privacy, the question that we have is that what should the epsilon be? That's the interoperability question. How do you explain, let's say, an epsilon to a person? Right? So there'll be an interoperability question in this case of explaining privacy budget. And similarly, you have data sets, different data sets at different levels of security requirements or different levels of inferences. How do you build secure mediation around something like that? To give you a little bit of scale, here is the data sets for which I sort of talked about earlier already. So if you look at, let's say, the UCI data set that we have generated, even for one building, we have approximately 2 events per second that arises, which is around 44,000 events per day. If you take a campus-level set of installation, which is, let's say, roughly, like Berkeley would also be at least 200 buildings. If you sort of take that, we're talking of something around 500 events per second. So you're sort of getting this much data in, and you're trying to build real-time services after ensuring privacy technologies inside it. And similarly, the queries, they're a mix of selections, aggregation, and join queries. In DBH, for the time when we are running the services, we roughly get about 10 API calls per minute. So that's the set of amount of usage. Now, we have not publicized the stuff too much. As the thing scales and goes over to the campus level, this will probably increase a lot more. So the question for us first was, can we design secure data management technology that can sustain such query and data rates? So if I go back to secure computing, there's a lot of work in secure computing that's happened. And if you look at it, ranging from homomorphic encryption techniques, ORM techniques, to deterministic encryption, to order-preserving encryption, and so on, there's a lot of work which is headed towards practical, let's say, security. And the problem with that is that it actually leaks a lot of information. If you go towards something which is much more secure, for example, homomorphic encryption with ORAM, the speeds of this are much, much, much slower. There are several orders of magnitude sort of too slow. There's more recent work on secret sharing mechanisms and MPC-based systems, which offer also very strong security guarantees, but they're also incredibly slow, several orders of magnitude slow. So just to give you a sense, the second column there refers to the time, and when I say sometimes X, that means that the technology takes that much overhead compared to, let's say, plain text processing. So the specifically interesting part of it here is if you look at let's say, multi-party computed MPC sort of engines, they are probably around 1 million times slower, which is 5 or 6 orders of magnitude slower compared to plain text processing right now. And if you sort of compare this to a strategy in which let's say, I've outsourced data and stored somewhere else, and we just download the whole data and sort of compute on the downloaded data, that is roughly around 10,000 times worse. So these techniques are sort of much worse than a full retrieval of data sets itself. Okay. So the key insight that we went after in terms of building or scaling technologies, and this applies both for secure computing, which I'll talk about now, and also for differential privacy as well, was exploiting partial sensitivity of data. So if I sort of look at data itself and the building data, think of, let's say, entry-exit data from a building. Going back to the example which I said, where there's inference about people, number of hours they work, that probably is sensitive because I can infer something which is useful from that data. But if I sort of am inside the building right now, the specific location I'm at probably is not that sensitive. Unless, of course, you're in a sensitive room or smoking lounge, then sensitive again. But a lot of the data that you sort of deal with is actually not sensitive at all.
Yes? Isn't location within building exactly what let you compute the tardiness of different faculty?
So in that particular case, in terms of, let's say, we want to hide the teaching schedule of yours, right? So the time when you enter into the teaching room, that instance of time might be sensitive. But if I'm sitting in my office, that's probably not sensitive. The part that I'm in the building is sensitive. And I enter the building and I leave the building, that's probably sensitive. So you can always take these data sets and sort of come up with strategies on figuring out what's sensitive and what's not sensitive. Okay. Similarly, example for surveillance video. So surveillance video cameras are there all the places, not sensitive. But unless somebody objects, so for example, I just signed a consent saying, hey, you can tape this thing today, so it's not sensitive. Had I not done that, even if the taping was going on, that would be sensitive. So basically, the key insight is you can sort of take data sets of this kind and decide sensitivity, non-sensitivity. And this is not a new idea. This is sort of, if you go back to the practice of privacy and security, that's sort of very commonly implied. So the question that we had was, can we exploit this to improve performance? So let me give you an example. So let's take the example from the perspective of secure computation. So here is an example of secure computation where we have, let's say, partly sensitive data and partly non-sensitive data, and I've divided them into two parts. Now, most of the data I'm assuming going to be non-sensitive. Some part of the data is going to be sensitive. And there's a query queue, which I run. So the query will naturally get partitioned into two parts. There'll be a query running on sensitive, there'll be a query on non-sensitive, and you'll collect the answers from both of them and construct the answer. Obviously, this leaks information. So here's an example of where it leaks. For example, if I retrieve tuple T2 from the sensitive side and the tuple T, in this case, I'm looking for John's record, T6 from non-sensitive side. The adversary has learned that T2 and T6 correspond to the same guy. So hey, T2 is actually John's record. You know that. Okay, what if I use a technique which is access pattern hiding? So a large number of techniques are access pattern hiding. They're expensive, but you pay the price, but sort of it can be done. What do you learn? We still learn the same. You learn that there exists a record from the output size. You learn the thing that, hey, John has a sensitive record, for example. So the question is, what's the security guarantee you want? So one way you can sort of look at this is, imagine I've got this world in which there's sensitive and non-sensitive data. What I'm trying to avoid is linkability between sensitive and non-sensitive data. I don't want them to be linked with each other. And furthermore, I don't want basically ciphertext. I want ciphertext indistinguishability. So I want ciphertext to be indistinguishable from each other. So that's sort of, you can formalize this property. So let's now look at the same thing and try to achieve a ciphertext indistinguishability and also non-linkability properties. So here's an example. So imagine what I've done now is I've changed the problem. Instead of sort of looking at the data, sensitive and non-sensitive data by itself, I'm going to actually bin them together. I'm going to create a sort of partition of both sensitive and non-sensitive data into bins. And when a query comes in, instead of for a query queue, instead of sort of retrieving one object or one particular bin, one particular data object or a particular value, I'm going to retrieve all the objects in the given bin, which is sort of, there's a sensitive bin, there's a non-sensitive bin, I'm going to retrieve both of them, okay? So at this stage, what does the adversary learn? The adversary learns that, hey, there is something between these two, there's some connection between these two bins. There's something that exists which enables you to sort of retrieve a sensitive bin and also a non-sensitive bin. But if you do this work a little bit carefully, what you can do is you can ensure that every sensitive bin is connected to every non-sensitive bin. If you actually achieve a complete sort of a bipartite graph in this particular case, what you get is the adversary will not be able to learn any association specifically between at the object level. Though even if he learns that a given bin and two bins are retrieved at the same time, you don't really get actually the fact that if every bin is possibly connected to every possible bin, then the adversary will not learn anything at all. So this technique can be shown to be essentially would not leak any information through either joint access or through output size attacks. Now, there are some challenges in workload skew attacks which can sort of happen, but you can even overcome that. So I'm going to run out of time, so I probably will not be able to give you the algorithm as to how to achieve such a bin. So let me skip past that, but let me show you a quick result. Okay, so here's the result. So very simple idea from a system perspective of binning things and sort of retrieving them together. Question is, how well does it work? Now in this bin, if you notice what I've done is instead of retrieving one object, I'm retrieving multiple different objects, basically trying to hide the access pattern or association between accesses by different people. So if you sort of develop a cost model for it, what turns out finally is a result right here, where if your sensitivity, which is alpha, the percentage of sensitive data is alpha, if this is less than, and this gamma is the amount of time it takes to encrypt something, to transmit one record on a network versus divided by the amount of time it takes for encryption. So if you take that gamma And there's also a square root of ns, which is the number of sensitive bins that you create. So this value typically is expected to be very small. So for most amount of, let's say, alpha values, which are the amount of sensitivity of data, unless the sensitivity data is around 99% data is sensitive, this approach will actually work very well. And it will perform better. From an analytical perspective, you can sort of show that. And here's a real result from basically running the experiments of the technique on two different techniques or two different approaches. So one was we applied a SGX-based sort of a hard, like secure computation. We applied query binning on top of it. We also took a MPC engine and applied query binning on it, and we can significantly improve the performance. The interesting part is not just that the performance improves significantly. It's also that with query binning, because access patterns are hidden and output attack is hidden, these techniques become more secure as well. And this is the experimental results. Let me skip it. There are a lot of assumptions that we sort of made, but about how the query binning technique will work, but then the paper sort of relaxes all that stuff. Let me give you one more thing, and then we'll be done with it. So this is the pitch for the differential privacy part again. So we used sensitivity of data, or non-sensitivity of data, but partial sensitivity to sort of improve on the performance of secure computing. The same idea can be carried over to also differential privacy. So here is an example. So imagine, again, the occupancy data that we had, and the query that I want to ask is, how many events with occupancy over 20 happen on this particular day? So this is a real result, basically real data which is coming in. And what you have to count is number of events which have occupancy of more than 20. Now, if I look at this data set, this differential priority data set with Pegasus, with in this particular case of salin equals 0.1, it's very difficult to sort of get this answer. The real data is this. This is the real data. So the question is, if you lose differential privacy, and maybe you can design specific differential privacy techniques for this particular part or for this particular question, but the utility of these queries, of these techniques, for answering these queries goes away. As the complexity of query increases, the utility actually goes very bad. So what can we do? So again, what we're going to do is exploit sensitivity. So I'll give you an example, and then I'll leave you with that. So imagine data sets at this stage can be partitioned into sensitive and non-sensitivity parts. So some data is sensitive, some data is not sensitive. Usually this is based on a policy. Okay? So one possibility is, let me just go ahead, when a query comes in, let me give you the results on the non-sensitive part as is, and use differential privacy for basically sensitive parts. But if you do that, what you can show is that you can actually lead to leakage as well. So what we did with the help of Ashwin and EOS, the student who sort of sitting there, so we ended up generalizing this concept of differential privacy to basically one-sided differential privacy. And the idea was that since I've got data which is both sensitive and non-sensitive, imagine the whole goal is to hide and provide guarantees to only the sensitive data and not to the non-sensitive data. So if something is sensitive, we want to ensure that remains I release the non-sensitive data in such a way that the fact that a particular data is not released causes a confusion or ensures uncertainty whether the data was not released because it was sensitive or because we just did not do it, because the mechanism sort of did not do it. So again, we can do this. I'm not showing results of it because this work is sort of in progress and under submission. But here's an interesting aside for this notion of one-sided privacy. So in this one-sided privacy, we're able to sort of publish not just necessarily the differential priority data or count data, but we can actually, since we are sort of publishing potentially nonsense data in its raw form, there's a whole new set of applications that can potentially be built around this. So imagine, let's say I've got video data or any kind of, let's say, multimodal data or even text data, and I want to sort of provide guarantees, strong privacy guarantees by sharing this data. So I can actually, using the OSDP or this mechanism, share parts of the real data while still maintaining essentially strong guarantees. So I can actually do things like summarization. I can extract some of the summaries, publishing multimedia data using this technique. All right, so I'm going to skip that and go straight to the conclusions, which is right here. Oops. Okay, so the conclusion is that we have a system which we built. The main message which I wanted to bring out was that as we integrate different technologies, new challenges arise and new opportunities for research arises. Thank you.
We have 2 minutes for, a few minutes for questions. Does anybody have any questions? Dick.
Yeah, so this concept of sensitive and non-sensitive data is very related to the idea of invariance in the census data. Although I'm very uncomfortable in having people decide what is sensitive and what is not sensitive, because historically they've gotten it wrong. Like one example comes to mind, AOL. It turns out a lot of things people claim are non-sensitive are just sensitive things they haven't figured out how to exploit yet. So do you have guidelines on how people would...
So there is a significant body of work which is sort of done, if you remember multi-level security, for example, at the time when this clearances were sort of coming up, or people coming with this multi-level security stuff, right? They had a similar kind of question that came up as well. And so there are a lot of work that's been done in trying to automate this process of selecting what's sensitive and what's not sensitive. I don't think it has succeeded in all cases. There are certain situations where people can apply some techniques, for example. So just give you a trivial idea in the mind. Imagine that this data, which is class schedule, is published on the web. Hey, that cannot possibly be sensitive for sure. Whereas if you have access control policies which dictate that, hey, some parts of people object to sharing some data, you can utilize that to sort of learn sensitivity versus not sensitivity in this case. So people have tried different things, but it's a good question. I don't think there is a clear-cut 100% answer to that particular question. Basically, the issue can be pushed around from the other perspective as well. So I have to build a system. I require to sort of publish data for this system. That's why it's a little different compared to, let's say, a traditional Census Bureau kind of situation where you publish data with privacy sacrosanct. Here, a system must exist. So I'm trying to do monitoring, or I'm trying to control HVAC control, for example. It's not that I can hide the data at this stage. Question is, can I at least prevent some inferences from happening? So the concept is a bit weaker.
I mean, there are some sort of obvious cases where it may be obvious. For example, if you think about census data, right? Group quarters, typically you think that their locations are known because they're physical entities and their addresses are known. But for example, certain group quarters like domestic violence shelters, their location should not be made public, right? So there you have a clear distinction between sensitive and not sensitive for the record. And yeah, there are some examples where
I think the point is you can get it wrong. That's true. That's correct. That's correct. We don't have a great solution. So if that's what he is saying, yes.
you just seem so confident about some of the examples. I was hoping you'd have
Be deeper insight on that thing. So in a lot of ways, if you think about it, the reason of the confidence comes from the fact that this is innocuous data. We have the data. It's not that you can do anything about it. Like you want Wi-Fi connectivity, you are connecting, I know where you are. So it's already there. The question is when I share it, can I share it a little bit more wisely? That's all.
You presented results earlier about predicting someone's location.
Yeah.
Using the model and the differentially private occupancy statistics. I didn't catch what was the comparison, like if you didn't use the differentially private statistics at all,
right?
Just based on the model,
right? I didn't show that to you. I didn't show that to you. Yeah,
Is there a significant difference there?
Yes,
Were the differentially private releases helping?
Yes. So two results there, right? So for two parts there, right? Because you can sort of look at it from a privacy loss perspective. Like, what if I gave you the exact counts, right? I think this question was asked earlier as well. Like, if I gave you the exact counts, how much would you have been able to guess? So from that, there's a privacy gain. Hey, if I give you differentially private stuff, how much do I gain? And the loss is, hey, from the prior, difference to prior to basically the differentially private one, right? So turns out that the thing I showed you was around 3 or 4 out of the 50, about 3 or more people I could get to know their location, which priors would not let you know. Priors worked well for about, if I remember correctly, for about 2 or 3 people. So from 2, it went to 4 or 5 with the epsilon equals 1. And so the other part is also how much loss was. So from the top, if I just give you counts, it was more like, if I remember correctly, around 10 or so. So there's some gain from privacy.
One more question? Okay, let's thank Sharad very much.